Hazardous Locations and the IEC. Part 1. IEC the Road to Harmonization. The science of fire and explosion can be quite complex, but the underlying principles are really very simple. Bringing together a flammable material or fuel with a source of ignition in the presence of the oxygen in the atmosphere will result in combustion. Depending on the particular mix, the combustion can be a slow and mesmerizing fire or a rapid and all-enveloping explosion. Since the earliest days of harnessing the energy available from the commercial development of petroleum resources, understanding the science of fire and explosion has been critically important. Advancement in the process industries that deal with the extraction, refining, and transformation of petroleum, as well as a wide range of other flammable manufacturing materials, has created an ever-increasing demand for controlling the flammability risks. One distinct area of concern has been that electrical equipment and its wiring could provide the source of ignition for explosive mixtures. Thoughtful engineering analysis, techniques, and specialty equipment would ultimately be required to effectively manage these risks. Over the years, many industrialized nations worked within their own economies to develop a national consensus on how to evaluate and classify the risks associated with the extraction, processing, and handling of flammable materials in the presence of electrical systems. The United States, often in collaboration with Canada and Mexico, developed a comprehensive set of rules for evaluating and classifying the risk of ignition from electrical sources in those areas that could have explosive atmospheres. This activity also produced regulations for the techniques and equipment to be used for these installations. They were then firmly aligned with the specialized product standards that were simultaneously being developed by consensus among industry engineers, technical committees, and third-party certification agencies. The North American approach for classifying the explosion and fire risks in these hazardous locations, frequently referred to as the class and division method, has been collected into a chapter of the National Electrical Code, or NEC, as well as corresponding Canadian and Mexican codes. Meanwhile, there were also alternative methods being developed in other parts of the industrialized world for dealing with these locations. Certainly, the analysis of the actual risk of fire and explosion would yield the same fundamental results, regardless of approach. But it is the method of classifying the risks and the engineering solutions applied that would introduce additional options in the development of electrical systems. Even though the underlying science would be the same, application of the principles to real installations requires detailed technical knowledge of the standards, codes, and procedures that are unique to a specific national jurisdiction. But it was the growth of international corporations and trade, as well as political and economic reorganization in many regions, that created the need to effectively address crossover electrical installations. The ability to coordinate the methods for these installations in hazardous locations fueled the drive toward worldwide harmonization as an important goal. Historical evolution of the standards that would influence the future engineering of systems and the development of products for hazardous locations typically began at a national level. They then moved on to multinational collaboration that is ultimately expanding to yield a fully international framework. What is now known as the North American approach toward hazardous locations formed around a working consensus among the United States, Canada, and Mexico. The European movement along the path from national to continental standardization was driven by enormous shifts in commercial, political, and economic collaboration. Eliminating technical barriers to the free flow and application of equipment in the European community forced the standardization of products and methods to become an essential part of the plan. By 1978, the Committee for Electrotechnical Standardization, or CENELEC, issued standards for use across Europe to improve coordination and blending of those that had been developed by individual countries. The resulting Euro norm or EN standards made possible the creation of the ATEX directives that were issued to establish essential health and safety requirements across Europe. ATEX, an acronym from the French for explosive atmospheres, is divided into two parts. ATEX 137 covers the requirements for installation, maintenance, control, and safety procedures for users and employers in the non-electrical operation of their facilities. But it is ATEX 95 that addresses the responsibilities of manufacturers and importers of electrical equipment for use in explosive atmospheres. It affects the design, production, certification, declaration of conformity, quality controls, and audit processes for these specialized products. The International Electrotechnical Commission, or IEC, is a 100-year-old organization of more than 80 member countries, whose mission is to develop and publish electrical and electronic consensus standards and assessment programs. Their efforts are dedicated to eliminating barriers to global trade that could be caused by conflicting national standards. Largely based on the work of Senelec, the IEC created a series of standards for explosive atmospheres that have now been embraced in a revision of the Euronorm standards, including renumbering for consistency with the IEC documents. An additional effort toward international harmonization was the creation of a comprehensive assessment program that could be used for implementation. Known as the IEC EX scheme, it provides a structure for authorization of certification agencies, called notified bodies, to be available to conduct examinations of products and manufacturing processes. The notified bodies would also conduct evaluations of the manufacturer's quality systems and controls, including the scrutiny of follow-up audits. The all-important test reports and certificates of conformity issued by these agencies provide the documentation for product nameplates and marking. Support for global harmonization continues to grow. The UN, through its European Economic Commission, promotes and encourages adoption of IEC standards and the IEC EX certification scheme among the Commission's 56 member countries. And in North America, IEC standardization has also received validation. Although the United States, Mexico, and Canada may be at different stages, revisions to each country's national standards over the past several years have included the path toward harmonization. For the United States in particular, progress toward harmonization led to the adoption of two new articles in the National Electrical Code, Articles 505 and 506, as alternatives for treating hazardous locations. These articles are very much in line with IEC standards. Part 2. Treating the hazardous location. There is no doubt that challenges can always be lurking in the details, but a clear sense of the underlying principles for dealing with electrical equipment in hazardous locations can bring them to light. The fact that the science and much of the equipment theory and technology are so similar between North American and IEC systems makes resolving the points of difference quite manageable and the transition less difficult. Four crucial elements guide the overall process for addressing the use of electrical equipment in hazardous locations, regardless of the system used. The first, and most fundamental, is conducting a risk assessment. This is an evaluation of the degree of likelihood that an explosive condition could develop in a process area or other location because of flammable material in the atmosphere. The second consideration involves selecting the type of technology and specific equipment to protect against the potential for electrical components becoming a source of ignition. Installation practices will also help guide the selection once the risk assessment has been completed. Manufacturers are responsible for assuring that standardized testing, assessment, and certification of the equipment they have engineered and manufactured are accomplished, the third element. And finally, manufacturers must adhere to audited quality, marking, and documentation standards that make certain all relevant application and conformity data are available to specifiers, installers, and owners. Part 3. Risk Analysis for Gases and Vapors. Risk analysis involves measuring the prospect that there is sufficient flammable material in the atmosphere to create an ignitable mixture. Starting with gases, vapors, and flammable liquids, referred to as Class 1 in the National Electrical Code, the North American approach has traditionally divided the risks into two categories, reflecting the probability that an ignitable mixture could occur. The first, Division 1, includes locations where normal operations could permit the flammable material to form ignitable concentrations in the atmosphere, either some of the time or perhaps even all of the time. In contrast, Division 2 describes locations where hazardous materials are stored, handled, or processed in ways that are unlikely to create ignitable mixtures when everything is operating normally. IEC 679, the principal underlying standard for harmonization, uses a similar concept for categorizing risks, but it splits the risk of ignitable mixtures during normal operations into two separate categories. Calling the categories zones, the IEC approach starts with Zone 0, defined as those locations operating normally that could create ignitable concentrations of gases or vapors continuously or for long periods of time. Secondly, there is Zone 1. This zone could still be expected to create explosive concentrations during normal operations, but not often enough or long enough to require a Zone 0 designation. The final zone, Zone 2, is identical to its North American equivalent, Division 2. Explosive concentrations are not likely to exist in the atmosphere under normal operating conditions, but failure or abnormal circumstances could cause a temporary risk of a flammable atmosphere. While the intention of the risk categories is certainly clear enough, those with the responsibility for conducting site evaluations or plan reviews to determine which risk category should be assigned often prefer to use a more quantitative analysis. There are unofficial numeric parameters that frequently serve as guidelines in the classification process. When the occurrence of ignitable atmospheres exceeds 1,000 hours per year, the risk would be judged to be Zone 0. Locations that were considered to be Zone 1 could experience explosive atmospheres between 10 hours per year and 1,000 hours per year. And under this method, when the issues occur less than 10 hours per year, the designation would be Zone 2. Of course, these parameters must be adapted to local practices, experience, and circumstances. Since it has a very important impact on the equipment that will be selected for the application, the risk analysis or classification of the hazardous location must also include information about the nature of the hazardous material that could be present in the atmosphere. Gases, vapors, and flammable liquids are assigned to groups based on the similarity of their explosion characteristics to the typical material used to represent the group. Within the North American class and division system, Group A is represented by acetylene, Group B by hydrogen, Group C ethylene, and finally Group D includes materials comparable to propane. The zone system has a similar method for dividing these hazardous materials into groups using the same explosive properties, but the letter designations are the reverse of those used with divisions. And in this case, both acetylene and hydrogen-type materials are pulled together under the designation 2C. Materials similar to ethylene are Group 2B, and those that have explosive characteristics corresponding to propane are designated 2A. The Roman numeral 2, appearing before each letter, indicates that these groupings of gases and vapors are not the result of underground mining, The special requirements for mining use the Roman numeral 1. Arcing and sparking that could result from the normal operation of electrical equipment is certainly a potential source of ignition, as is component failure. But there are also many types of electrical equipment, lighting fixtures, for example, that can produce sufficiently high temperatures to become a source of ignition. For this reason, a full risk analysis must also include information about ignition temperatures of the gases and vapors that could be present. Both the division and the zone systems use identical temperature codes, although the zone system relies on fewer steps. Part 4. Methods of protection and equipment for gases and vapors. Recalling that the fire triangle brings together the three essential components for combustion to occur: fuel, oxygen in the air, and a source of ignition, it is now possible to begin addressing the explosion potential identified during the risk analysis. A variety of approaches are available for the design of these specialized electrical installations. These are made possible by the alternative protection techniques that provide equipment options for the specific hazardous locations. The range of protection techniques can restrict the presence of the combustible mixture, isolate or reduce the energy of the source of ignition, or safely contain or quench combustion that could be initiated by the electrical device. Within these general approaches, there are 4 basic concepts of protection, each with one or more engineering solutions. The individual solutions have been assigned a simplified type symbol to make identification and specification easier and more consistent. The first concept includes equipment that has been constructed taking extra measures to produce no arcing, sparking, or high temperatures. These are known as increased safety devices, type E. The use of additional clearances, spring-loaded terminations, and physical protection provide a method that can be applied to standalone terminal and connection boxes, or in conjunction with other methods, such as those used for controls, motors, and lighting fixtures. Another approach has been developed around the concept of containing, quenching, and safely venting